All right, next application. We're going to look at something called a Hamming code, or in general, error correcting codes. Now, when I say code, this has nothing to do with a secret code, like for cybersecurity or cryptography or something like that. That is also another application of linear algebra, where you're figuring out how to combine a message with a secret key and decode it on the other end so that no one can observe your message if they intercept your transmission. This is a different kind of code, but every bit is important. And the purpose of this kind of error-correcting code is, just as the name would imply, we are going to correct errors, particularly errors in transmission. So as you probably know, any information that we want to send digitally over the internet or whatever has to be reduced to bits, right? It's reduced to ones and zeros, and we humans have figured out how to take almost anything we want to send, whether it would be text, whether it would be an audio file, whether it would be an image, whether it would be a video file, or anything else, and basically encode it in a series of ones and zeros so that it can be interpreted on the other end and reconstituted into whatever form the information was supposed to take, right? Now, the problem, of course, is that when we are sending information across long distances, or actually it doesn't even need to be that long a distance for this to happen, there is the possibility of corruption. And corruption simply means that some of the bits have a possibility of flipping from 1 to 0 or from 0 to 1 in transmission so that the receiver does not get the exact message that we sent, okay? And of course, we're not going to know which ones were flipped the opposite way, right? It'd be easy if we could send you the message and then say, oh, by the way, bits number 3, 17, and 245 were wrong. Then the receiver could just say, oh, okay, well, then I'll flip those from a 1 to a 0 or from a 0 to a 1, and then I'll be back to whatever the original message was, right? We're not that lucky. We're going to get a bunch of bits in a row, and we're not going to know which of them, if any, has been corrupted. And our job is to be able to do the following things. A, detect which bits were corrupted. And B, correct them so that we can put the message back the original way that it was sent. Now, at first glance, this seems impossible, right? Because if I get a bunch of bits from you and some of them, I don't know how many and I don't know which ones are corrupted, how in the world would I be able to reconstitute your message, right? Turns out there is a way, though, and these clever codes, the first one was invented by Hamming, called the Hamming code, is a way to do that. So let me draw a little picture here. If I have a sender over here, and I have a receiver over here with a closed head, and each one of them has a computer or some sort of digital device, right? I'm going to be sending a string of bits here, and this part in the middle is often referred to as a noisy channel. And when we say noise, what we mean is corruption. What we mean is that what's sent over here is 1101001110. But maybe what's received over here is 1100000111. Let's put that in red. 1. So we are getting some corrupted bits. And so the idea is we're going to have to figure out how to look at this thing that we got without any information about what the sender sent other than these bits and figure out, aha, that one was wrong and that one was wrong. So I'm going to flip this one back to a 1, flip this one back to a 0. Then the rest of the message is exactly what it was. Let's see, 110100. I messed that up. But you get the point, right? 1101001110, and so we can get back the identical message. This is more important in some situations than others, right? So if you're streaming a movie and a few of the bits, the right kind of bits, get messed up, it turns out not to matter that much because it's just one frame in a whole movie that's flying past. And if one of the pixels is a slightly wrong color, you're never in a million years going to notice that, right? But there are certain things for which it matters quite a bit, right? So imagine if you're sending a credit card number and part of the credit card number got corrupted. Well, that certainly wouldn't be good. Imagine if you're downloading an app or an executable. If there's any part of that code that's wrong, that has a single bit wrong, it could cause your computer to malfunction. It could cause it to delete stuff. I mean, you know, put a virus on your machine. There's all kinds of things that could happen if any part of that executable is wrong. So we are going to design a code that makes it not foolproof, but for certain kinds of errors foolproof. And if we can get a bound on how often errors happen, then we can repair the text to a great significant degree, as we'll see when we look at some examples. All right. So let me first introduce you to a couple things here. First of all, I want to talk about, and this seems off topic, but it's really not. and that is the concept of doing matrix vector multiplication. But we're going to do it a special way with this application. We're going to do it in mod 2. Mod 2 arithmetic essentially just means that all of our numbers are going to be zeros and ones. And what we're going to do is we're going to say if we have a 1 times a 1, that's going to give us a 1. If we have a 1 times 0, that's going to give us a 0. If we have a 0 times a 1, that's going to be a 0. And if we have 0 times 0, that's going to be 0. Okay, so all that is just exactly what you'd expect. There's nothing new there, right? Let's do plus. If I have a 0 plus 0, I'm going to get a 0. If I have 0 plus 1 equals 1. If I have 1 plus 0, that answer is going to be 1. Now, up to this point, you're like, why are you even telling us, Stephen? We sort of knew all this since first grade or before. Here's why. What happens if we say 1 plus 1? What's that going to equal? And that turns out to be the trouble spot, and we're going to repair it in a very simple way. The way we're going to repair it is to say that this is going to give us 0. Okay? 1 plus 1 equals 0. Who knew? And essentially what we're doing is we're taking our answer, but then we're computing the remainder when divided by 2. That's essentially what we're getting. That's how we get the 0 there, right? So if you add up a bunch of stuff and you get the number 13, the answer for us is going to be 1, because 13 divided by 2 gives you a remainder of 1. Whereas if we add a bunch of stuff up and we get 14, that's going to give us the number 0, because if you add up a bunch of numbers and get 14, or take 14 divided by 2, that gives you a 0 remainder. So really all that's going on here is we're essentially counting the number of ones that we have if we're doing a long number of additions, and we're figuring out whether we have an even number of ones or an odd number of ones. Okay, so let's do an example. Suppose we have this vector 1, 1, 0, 1, 0, 1, 1. And let's say we're going to take the dot product between that and this vector, 0, 1, 0, 1, 1, 1, 0. And notice I've made one a row vector and one a column vector, so we get a scalar here out, right? All right, what's this answer going to be? Well, it's going to be 1 times 0, which is 0, plus 1 times 1, which is 1, plus 0 times 0, which is 0, plus 1 times 1, which is 1, plus 0 times 1, which is 0, plus 1 times 1, which is 1, plus 1 times 0, which is 0. And all that is going to turn out to be 1, because there is an even number of ones here, right? Because remember, we're going to say 1 equals 1, 1 plus 1 equals 0, 1 plus 1 plus 1, that's the same as 1 plus 1 plus 1. Which is the same as 1 plus 0, because remember 1 plus 1 equals 0. And 1 plus 0 is going to be equal to 1. 1 plus 1 plus 1 plus 1, by the same logic as 0. 1 plus 1 plus 1 plus 1 plus 1 equals 1, etc. Right? So it basically just comes down to how many ones do you have. If you have an odd number, the answer is going to be 1. If you have an even number, the answer is going to be 0. That way it restricts all of the values that we're going to be working with to the binary numbers 0 and 1. Okay, so that's the first just little bit of bookkeeping you have to get out of the way, and that will surprise you if you're not ready for it, because all of the operations we're going to do with these Hamming codes are going to be in binary, and therefore we're going to be doing all the addition and multiplication mod 2 is what it's called. We're doing it all in mod 2, which means we're going to get zeros and ones. Okay, now let's talk about how the code works. Here's the deal. Let's say I have a message 11001011010101. Let's say that's our message. The first thing we're going to do in the Hamming code is we're going to divide this into so-called nibbles. And in computer geek talk, 4 bits is called a nibble. Sometimes it's written like nibble with a Y. I usually put an I on it. And by the way, 8 bits equals a byte. So a nibble is kind of like a little byte. Get it? So 4 bits is a nibble. Fun fact. Now you can sound like a nerd to your friends. Okay. So no matter what message we're sending, no matter how long it is, and boy, if this is an audio file or a movie or a bunch of pictures from your vacation or whatever, it is going to be very long. But no matter how long it is, we can divide it up into chunks of 4, right? And if it turns out not to come out even, like if our message was 0, 1, and then stopped there, we can always just pad the end with zeros or something like that, right? So it's a very easy job to take a huge long string of bits and divide it into groups of 4. Okay, now what we're going to do is we're going to take each group of 4 and we are going to send it through a function, and this is actually going to be a matrix, and I'm going to call this thing G transpose because we're going to have a matrix called G, and when you transpose it, we're going to multiply that by this vector. That's how we're going to get this thing out. But if over here I have the thing I want to send, which by the way is called the signal, so it's going to be 4 bits long, and if we send a long message, we're just going to do this again and again and again and again and again for every sequence of 4 bits. We're going to basically feed that into our little function, and out is going to pop an answer, and this answer here is going to be 7 bits long. And it is going to be what's called a code word. Now, not every 7-bit sequence is a code word, as I'll explain. A code word is a 7-bit sequence that will come from a 4-bit sequence that's the signal. Not all 7-bit sequences come from 4-bit sequences through this thing, as I'll explain in a minute, so just kind of hold on a second on that. But this basically is going to be a 7-bit thing, and it's that 7-bit thing that we are going to send across the noisy channel. So going through this noisy channel, and there's going to be some corruption here, is going to be a 7-bit thing. 1, 2, 3, 4, 5, 6, 7. Okay. All right. So we take a 4-bit thing, we run it through our G transpose function, and we get out a 7-bit thing which we send across the noisy channel. Now, the person on the other end is going to do 2 things with the 7 bits they receive. The first thing they're going to do is they're going to run it through an H function. I'm not totally sure why they call it H or G for that matter, but they do. And this is what's known as the checker matrix. Checker meaning something that checks, not like the game. And what's going to come out is going to be a 3-bit thing. So kind of wild here, right? We got 4 bits here, and that goes and converts into 7 bits. We send that across the wire. We put the 7 bits into this H transform here, and we get back a 3-bit thing. And that thing goes by the name of the error syndrome, which we'll be discussing quite a bit in just a moment. The second thing we're going to do is take those same 7 bits, and we're going to run it through something called R. And R is another transform, which basically is G transpose in reverse. And we get out a 4-bit thing. And this 4-bit thing is going to be our decoded message. But this might be corrupted. And so what we're going to do is we're going to say, look at this error syndrome, and believe it or not, through the magic of the way these matrices work, this error syndrome is going to tell us whether or not these 7 bits were legit. Kid you not. These 7 bits that we get across the wire, which there's no way, seemingly, we could know if there's anything corrupted about them, this H matrix has the power to tell us if it is corrupted. And if it is corrupted, then what's going to happen is we're going to fix it here before we send it into the R matrix. And so when we send it into the R matrix, we're going to get back 4 bits, which, under certain conditions that I'll discuss, is guaranteed to be the right answer. So when I say this might be corrupted, what I mean is if we had sent these 7 bits that we got across the wire directly into the R matrix without looking at the error syndrome first, then it might be corrupted. But since we're looking at the error syndrome first, guess what? We are going to be 100% certain, subject to certain conditions, which I'll discuss, that we have gotten an uncorrupted message and we have gotten the complete thing. All right? So let's discuss how this all works. First of all, let me give you the G transpose matrix. And it looks just like a bunch of nonsense, and in a sense it is. This is a 7x4 matrix, which you knew, right? Because in that picture before I said we had 4 bits going in to G transpose. and we're going to get out 7 bits. And by the way, the reason I keep saying transpose is because that it's just, we're always going to end up using the transpose version, so it doesn't really seem useful to talk about G itself. They sort of designed that funny, I think, when they sort of present it. It makes sense to think of it as G transpose. Anyway, this is it. 1 0 1 1. 1 1 0 1. 0 0 0 1. 1 1 1 0. 0 0 1 0. 0 1 0 0. 1 0 0 0. That is the G transpose matrix. And I think you'll agree that if I do the vector multiplication with that matrix and a vector of any 4 bits, this will pop out a 7-bit thing. And that is exactly what we're showing in our picture here, right? 4 bits in, 7 bits out. That's exactly what's going to do. This is the thing that we want to send, right? This is our signal. This is our message that we want to send. And out here is going to be a code word, which is going to be in 7 bits. Now, let me talk a little bit about code words here, right? So, if you think about it, there are far more 7-bit vectors possible than there are 4-bit vectors, right? In fact, if you've taken all the math volume 1, you know how to compute this, right? Or maybe you can figure it out anyway. How many different 4-bit messages are there that we could send? And the answer turns out to be 16. That's 2 to the 4th. So we could send 0000, we could send 0001, we could send 0010, we could send 0011. And there are 16 total different 4-bit vectors that we could send. That's our whole vocabulary. It's kind of interesting to think that no matter what you wanted to send, even if it's an emotional plea or even if it's a political advertisement you've created in some class or whatever, you can break that down into a bunch of 4-bit things, each of which is one of only 16 different values. And that is enough to communicate anything that can go across the internet or anything that can be stored on your computer, right? So there are far more 7-bit vectors, right? Because the number of 7-bit vectors possible is 128, which is 2 to the 7th. So if you think about it, this is the situation we have. Let's say this is the space of all possible 7-bit vectors, all possible 7-bit quantities. One of the things in here is 0011010. Another thing in here is 0000000. Another thing in here is 11101111. Another thing in here is 11000101, etc. Right? There's 128 things in this box. But of those 128 things in a box, only a certain number of them could possibly be gotten from a 4-bit code word, right? Or, excuse me, a 4-bit signal. Because if you think about it, we've got our G transpose thing here, right? There's only 16 different possible things that we could put in here. And we know that each of those things that we put in here is going to have one answer, right? So there's only 16 different 7-bit vectors we could possibly get as an output to this thing. There's 128 7-bit vectors, excuse me. There's 128 possible sequences of 7 bits. And yet, only 16 things are in this box which are derivable from this matrix. And that turns out to be the thing that's the key to the Hamming code. Because what we're going to do is we're going to take that 4-bit vector and we're going to convert it into a 7-bit vector. And we're going to know that if I send that 7-bit vector across the wire, there's only a small number of 7-bit vectors that could be the real one that the person sent. Because if I get any of the other, whatever 128 minus 16 is, 112, if I get any of the 112 other ones, then I know that something was corrupted, right? So think about that. We can tell whether or not we can tell whether or not the message we received was the same as the message the person sent, because we know there's only 16 possible right answers. And if we look at those 7 bits, and if we say, well, you know, these 7 bits you can't get those from any of the 4-bit inputs to that G transpose function. If you tried all 16 different things that you can give as inputs to that G transpose function, none of them give this 7-bit output. We can right away raise a red flag and say we know something was corrupted. So that's our error detection, right? And so right here, if you look at this picture, that right there is the set of code words, this yellow box, okay? The code words are not any 7-bit vector. The code words are only the 16 7-bit vectors that are possible outputs to this function. Any other 7-bit vector we know is wrong, okay? Now, let me give one caveat here. If I had a message and I sent those 7 bits across the internet, if I sent that 7-bit code word, and any one of the bits was corrupted, it turns out I am going to get a non-code word. And that's because Hamming was smart. Hamming set this up so that when you look at the 16 different 7-bit vectors that are possible to get out of that G transpose thing, all of them are at least 2 bits away from each other. Okay, so to put that visually, let's say, I'm going to say suppose that 1100101 is a valid code word. Now, I don't know if it is or not. I'd actually have to check. I don't have it memorized. But let's just say for a second that that is a valid code word, which means there's some 4-bit signal, there's some 4-bit input that when you stick it through GT, you get out 1100101, right? That's what it would mean to say this thing is a valid code word. Okay, suppose that's a valid code word. Then I can tell you right now that this is not a valid code word. And the reason I know that is because that is only 1 bit different from this. And no code words are only 1 bit apart. I can tell you right now this is not a code word. Because that is only 1 bit different from this. I can tell you right now this is not a code word. Because that is only 1 bit difference from this. So the point is that the way Hamming set this up was that every 2 code words are at least 2 bits away from each other. And that's crucial, because that means as long as only 1 bit is corrupted in transmission, we can detect the error and we know something was wrong. Okay? That's the subject to additional constraints and assumptions that I was talking about earlier. If there's 2 bits that are in error, if I send a 7-bit thing across the wire and 2 or more of those bits get corrupted, all bets are off. And I might, on the other side, say, hey, I've got these 7 bits, and these 7 bits are a valid code word, so it must not have been corrupted. And I'd be wrong. Because really what happened is it was so corrupted that it actually corrupted into another valid code word. And then we're going to know something's wrong. There are more sophisticated error schemes built on top of the Hamming code that are able to detect multi-bit errors and even correct multi-bit errors. So we're not going to go into that with this simple lesson because I'm just going to be describing sort of the most basic code. But the assumption here is that when you send it across the wire, at most 1 bit is in error. And if that's the case, we can automatically detect it. Turns out we can automatically correct it too. And here's the deal. Suppose I take my H matrix here. And by the way, this is the H matrix. This is a 3x7 matrix, which you already knew because remember, 7 bits come out of the noisy channel and get run through H and produce 3 bits. So you know if I'm going to multiply this thing by something, I'm going to have to be multiplying it by something that is 7 bits long in order for this matrix vector multiplication to make sense. And you know that the result of that is going to be a 3-bit thing, which is what I want. And again, that is called the error syndrome. It's kind of a weird word. Okay? All right, so here is the H matrix. 0, 0, 0, 1, 1, 1, 1. 0, 1, 1, 0, 0, 1, 1. 1, 0, 1, 0, 1, 0, 1. Okay, does that look like gibberish? It's a little bit less gibberish, and you might recognize if you've done binary numbers before that that right there is the binary number 7. That column is the binary number 6. That column is the binary number 5. That column is the binary number 4. That column is the binary number 3. That column is the binary number 2. That column is the binary number 1. So, fun fact, it is the numbers 1 through 7 encoded as columns here. Okay? Now, here's the deal. When Hamming came up with his G matrix, and we use the G transpose, and his H matrix, he did it for a reason. And here's the deal. If we take H and we multiply it by a code word, So let's say for the moment that this thing here, this 7 bits in a row, is a valid code word. Now that's by no means the case for every 7-bit string, right? In fact, the vast majority of 7-bit strings, 112 of them, are not code words. But we know that 16 of them are. So here's the deal. If I multiply this H matrix by a code word, what I get out is this. Okay? So what that means is, you ready for this? It means that the code words are the words that are in the kernel of H. Remember, the kernel, or the null space of a matrix, is the set of vectors where, if you multiply the matrix by that vector, you get the 0 vector. So what happened is Hamming constructed this thing so that the kernel of H would be the code words and only the code words. So the way we do detection, you just sort of have to take my word for this. You could try all 16 of them and make sure it works out, and you could try all 112 of the non-code words and make sure that none of them give you 000, right? But anyway, or you can take my word for it and believe that Hamming was smart and worked all this out. But the point is that that's how we can do error detection. 1-bit error detection is we know that if we take a 7-bit string, we multiply H by it, and we don't get 000, whoa, something's wrong. That thing is not a code word. And therefore, we know that that 7-bit string is not what the person sent across the internet. At least one of those bits must have been messed up, right? Now, furthermore, the thing about this that's so cool is that if I multiply by this thing and I don't get 000, I know there's an error, right? Let's say I multiply this and I get 010. You know what that tells me? It not only tells me that there is an error, but it tells me that bit number 2 was the one in error. Whoa, are you serious? Yeah, because that is the binary number 2. If my error syndrome is 011, that tells me it was bit number 3 that was an error. If my error syndrome is 110, that tells me that bit number 6 was the one that was an error, because that is the binary number 6, and that is the binary number 3, and that is the binary number 2, and that works for any of them. The only way I know that there were no errors is if I get 000 here, which means there were no errors, right? By the way, in case you don't know how to do binary, just realize that a binary number, so if I take this and I kind of pivot it, right? So I'm looking at it like this, 011. Just realize that that first bit there is the 4's place, and that second bit there is the 2's place, and that lower order bit there is the 1's place. So the only thing you're doing when you're figuring out what number this is you're saying, well, that's 1, and that's 2, so we've got 3, and then we got a 0 in the 4's place, so the total thing is 3, right? And here we say we have 1 in the 4's place, 1 in the 2's place, 0 in the 1's place, therefore this is the number 6. So that's how you convert the binary thing, right? All right, so here's the deal. We're going to get our 7-bit thing on the receiving end. We're going to run it through the H matrix. If we run it through the H matrix and get a 0 error syndrome, we're like, boom, code word, love it. And therefore, we're going to take that thing and we're going to decode it using the R matrix, coming in a moment, and we're going to get the right answer. And we're going to feel confident that we got the right answer. Because unless there was more than 1 bit corrupted in that thing, which was our underlying assumption, we're never going to have more than 1. Unless there was more than 1 bit corrupted over the wire, we can feel confident we have the right answer. If, on the other hand, we get that 7-bit thing, and we run it through the H matrix, and we get a non-zero error syndrome, then we're going to say, no biggie. I get back a number from the error syndrome, right? Let's say it's 101, which means that bit number 5 is an error. So that means all we have to do is take those 7 bits we got over the wire, and we just got to flip bit number 5. If it was a 1, make it a 0. If it was a 0, make it a 1. And now we've corrected it. And now we can take our revised 7-bit thing that has that bit corrected and run it through the R matrix, and then we can feel confident that we've gotten the right answer. So even if the sender sends something and a bit is corrupted, we don't have to say, oh, a bit was corrupted, sender. Can you please send that again? We don't even have to ask them to send it again. We can just correct it on our own. Because we can say, man, the error syndrome tells me which bit was screwed up, and I can just unscrew up that 1 bit and I'm good to go. Oh, amazing. Can you believe this works? Let's check this out with the R matrix here. So the R matrix, which must be a 4 by 7. And that's because we know from the picture that we're going to take our 7-bit thing, which we've corrected if necessary. That's so important, I'll even put it on here. Corrected if necessary. And the way we know whether to correct it and the way we know how to correct it is coming from the H matrix. We're going to take that thing, we're going to run it through, we're going to run it through the R matrix to recover the answer, and that's going to pop out our 4-bit thing. So, in order for that to make sense, again, we would have to take our 7-bit thing here, 1, 2, 3, 4, 5, 6, 7, which has been corrected if necessary, multiply it by 4 by 7, bada boom, and we get back our answer, which is a 4-bit thing, which is what the recovered signal is. Okay? Now, you might be able to figure out what the R matrix is just by looking at the G matrix, and that's actually worth doing. I'm just going to kind of do this because I don't want to spend all day on this video, but I'll go ahead and just write it down what it is here. But it's interesting because actually looking at the G matrix, you can kind of figure out how to do this, and that's because 4 of the rows of the G matrix ended up recording just 1 bit of the answer. If you look at that G matrix, 4 of the rows just had 1 1 in them. And if a row has 1 1 in them, then that means when you dot product that row with the 4-bit signal, you just get 1 thing back, depending on whether that 1 position was a 0 or a 1. And so all we have to do with this R matrix is essentially decode those. And what we're doing here is we're saying, was the last bit a 0 or a 1? Whatever that answer is, put it there. Was the second last bit a 0 or 1? Whatever that answer is, put it there. Was the third to last bit a 0 or a 1? Whatever that is, put that answer there. And then was the third row's bit 0 or 1? And whatever that is, we're going to put the answer there. So this ends up decoding it lickety-split. And so if we take our 7-bit code word, which either was a code word we got or was a code word we made by correcting a screwed up 7-bit thing that we got, we're going to end up getting the answer on the other end. All right? So let's do an example and see how this works. Let's kind of put this down to a brass tacks. So suppose you receive 0, 0, 0, 1, 1, 1, 1. What do you do? And the answer is this. First, you run the H matrix. Run the checker matrix. So we do that, and we take our H, which is 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, and we multiply that by our message that we got across the wire, which may or may not be a code word. We're not sure, but this is going to tell us. And what we do is we take the ordinary matrix vector multiplication, so we multiply this by this, and we get 0, I think you'll agree. We take the dot product of the second row with this, and we will get 0, I think you'll agree. And we just do that one to make sure you get that one right. So that's going to give us 0 times 0 plus 1 times 0 plus 1 times 0 plus 0 times 1 plus 0 times 1 plus 1 times 1 plus 1 times 1. Okay? So that's 0, that's 0, that's 0, that's 0, that's 0. This is a 1 and this is a 1. So what's 1 plus 1? It is 0. So we had an even number of 1s here, therefore the answer is 0. And if you apply the same reasoning to the last row, you will say, that ends up also giving us 0. So this gives us a big smile on our face because we know, as long as there was not more than 1 bit corrupted, that this is, in fact, the very thing that they sent. And therefore, all I have to do is run this through our R matrix. And our R matrix, you'll remember, is 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0, 0, 0, 0. If we run that times that vector right there, we're going to get out a 1 and a 1 and a 1 and a 0. So that tells us that this is what the sender sent. And I will not do this on video, but I will give you the opportunity to do so. If you take that thing right there and you multiply G transpose by it, you will, yea verily, get 0, 0, 0, 1, 1, 1, 1, which is, in fact, the 7 bits that we got over the wire. Okay? So that's an example of a happy case. Now let's do an example of a sadder case. Let's say you receive 0, 1, 1, 0, 1, 0, 0. Let's say that is the word that we received. What do we do? First, we run it through our checker matrix. And so again, we have as our checker matrix 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, and 1, 0, 1, 0, 1, 0, 1. We're going to multiply that bad boy by our 7 bits, which may or may not be a code word. And we're going to discover that it's not a code word, because if you multiply that out, and I'll let you do that on your own, you're going to get 1, 0, 0. So this is a sad face. But wait, we're happy anyway, because the error syndrome is 4. And make sure you get your binary number there, right? We have a 1 in the 4's place, and we have 0 in the other places. Therefore, this is 4. So what that tells us is, boom, that guy is the one that screwed up. Because this is bit number 1, 2, 3, 4, 5, 6, 7. And the fact that we got an error syndrome of 4 tells us that that's the one we need to correct. So what we do is we say, I received that, but you know what? That is really the thing that is messed up. And therefore, what we're going to do is we're going to say, great, fix it, which is what we just did there. And the answer turns out to be 0, 1, 1, 1, 1, 0, 0, because we fixed that one guy there. And now decode it. And so now we run it through our R matrix. And our R matrix, as you recall, was 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. And if you run that through the thing, you will get back a 4-bit answer. Sorry, we got to multiply this fixed vector by it, right? So let me make that more explicit. So we're going to multiply by 0, 1, 1, 1, 1, 0, 0 with our fixed guy. And what we get when we do that, let's just do this. So we multiply this, we're going to get 0. We multiply this one, we're going to get 0. We multiply this one, we're going to get 1. We multiply this one, we can get 1. And so the answer that they must have sent was 0, 0, 1, 1. And that tells us what the answer is. So even though our error syndrome was not 0 and we knew something got corrupted, we were able to figure out how it was corrupted and able to get the right answer. And I'll tell you that if you take that answer we just had, 0, 0, 1, 1, and if you run it through the G transpose matrix, yea, verily, you will get 0, 1, 1, 1, 1, 0, 0, which is the thing that went across the wire. All right, extremely powerful concept. And in fact, every day, in fact, right now, as you're watching this, your computer is using this very kind of technology. It's using this exact math type of operation in order to say, hey, every single packet I'm getting across the network, I need to make sure that every single bit of it was not corrupted. And so it's able to look at that and automatically correct it. Just to show you kind of the impact of how this works, I wrote a little program here. And I was able to, I took a message and I encoded it all into bytes, okay? So I took basically every letter of the message that I was going to encode and I turned that into 8 bits, because the way that most text is sent across the internet today is they have a code called the ASCII code, which maps every letter of the alphabet and punctuation mark and digit into an 8-bit code. So what I did was I took my message, converted it into that 8-bit code, and then I ran a little program that would corrupt bits randomly in it. I corrupted bits randomly, and then I said, okay, let me pretend this is what I got on the other end, was this corrupted text that came through the normal channel, or through the noisy channel, rather. And what I did was I said, first, let me just plain decode it, not doing any error correction, not using the H matrix, not using the error syndrome. I'm just going to decode the thing and see what I get. And then I'm going to run it through the decoder, and I'm going to make sure that I check each error syndrome. And every time there's an error syndrome, I'm going to make sure that I fix it before I run it through the R matrix to get my answer back. And I just wanted to show you the difference here, right? So here's the first one. That's what happens when I decode it without cleaning. This is my message that I encoded. Now, I don't know if you can tell what it says. You might be able to look at it and kind of see a little bit of stuff here. Like here, maybe you see the word wakes. And here you see the word take. There's a little nigh or something. We, my. So there's little bits of it that maybe look like you could sort of get the answer through. But that's what happens if you take the noisy channel text and assume it's correct and simply decode it here, right? And now here's what it looks like when I do the Hamming decoder. And you can see that it is enormously fixed. There are still a few little goofs. Like I noticed this one here. The horn that wakes the sleepers, it looks like it corrupted my E into a $sign there. Over here, I saw for this jite and all the nights to come, so it messed up that N into a J right there. I think I saw one other one. Where was it? Can't see it off the top of my head. But those are indications where I had a 2-bit error. Out of the 7, right? And so that's where the Hamming code breaks down, because the Hamming code says, here's the deal. We're going to assume that there's never going to be more than 1 bit in error per 7 bits. And what happened is that corrupted text, I set the amount of corruption such that it was always able to, or not always, but most of the time, able to correct it and detect it. The only way an error can slip through and not be corrected is if it has more than 1 bit in error out of the 7, and that's where you need a more sophisticated code to be able to fix that.